Today we are talking about finding the inverses of functions and what inverses of functions do relative to their functions. So let's start with a function first. So imagine a function as a machine or some sort of process. You plug something in, you throw some input into the machine, and then the function does some stuff to that number. It might triple it and subtract 7, or it might square it and add 11. It could be anything. But whatever it does the same thing every time. So you plug in a number, you triple it and add 3, and you get an output. Every time you put a new number into the machine, it does the same steps in the same order, and a new output comes out. So depending on what you plug in, you'll get a different number out every time. But if you plug in a 12 every time, you'll get a 37, let's say. So every time I plug in a 12, I'm going to get a 37 no matter what, because this function is doing the same thing every time. So if we think of functions as machines that turn inputs into outputs, then the inverse of a function is the machine that turns the outputs into inputs. So if y equals 2x plus 3 is our function, then this function doubles the input. That's what the 2x does, right? Takes the input, doubles it, and then adds 3. If I want to find the inverse of that, I need to get x by itself. So we're going to subtract 3 and divide by 2. So we end up with this expression. X equals y minus 3 over 2. This equation takes our original output, subtracts 3, and divides by 2. And the result is our input, right? So if this is the input, and this is the output, then this is the same output from before, and this is the same input from before. We're swapping places. This is the inverse function right there. Does the exact opposite steps in the opposite order to get us back where we started. So if a function takes inputs and makes outputs, an inverse takes outputs and tells you what the input was. Okay, so here is that same function and inverse. Because they're swapping inputs and outputs, you'll notice that the domain and range of the original function are the domain and range of the inverse, but switched. So the domain of our function becomes the range of the inverse, and the range of our function becomes the domain. So the inputs and outputs switch. That's all it is. If you look at these two tables, you'll see that the red one is the same as the blue one, but the rows have been flipped, right? So instead of x being -2, -1, 0, 1, and 2, now y is -2, -1, 0, 1, and 2. We've swapped the inputs and outputs, and what that does graphically is reflect the graph across this line, y equals x, right? So if we're flopping all of these points, flipping them across that, mirroring them across this line of reflection, y equals x, the blue is our original function, and the red is the inverse. If you looked at each of the coordinates of each of these points, you swap the x and y coordinates, you get these points down here. So let's look at this one. This is what, 0, 3? So that means that 3, 0, 1, 2, 3, 0 would have to be a point on the other function, which it is. Okay, so inverses and functions have ordered pairs that have swapped or switched x and y coordinates. Okay, so let's find an inverse. This is the algebraic part. How do we actually do this? So first thing I always do is I rewrite it as y and x instead of f of x. It means the same thing. It's a little bit easier to work with. Okay, then the important step is to swap x and y. I'll call that step 1. So this is now going to be x equals 3y minus 1. I'm literally just swapping the x and y. I'm not changing anything else in the equation. Step 2 is to get y by itself. So we got to add 1 to both sides. Let me change colors so we can see what I'm doing a little bit better. Add 1 to both sides. So x plus 1 is equal to 3y. Then I'm going to divide both sides by 3. So y is equal to x plus 1 over 3. The third step in this process is to rewrite in function notation, which just means f of x. However, I can't write it as f of x because this was f of x, and I can't have them both be f of x because they're not the same thing. So the way we show that it's an inverse is we raise it to this -1 power, and we read that out loud as the inverse of f of x is equal to x plus 1 over 3. But the reason we do that is it does a couple things. It, one, links these two, so I know that this function and this function are related because they're both named f. I know that this one is the inverse because it's raised to the -1. So I know that this is the original and that this is the inverse. Okay, so to show an inverse, it's f to the -1 of x, but we read it as the inverse of f of x. Go ahead and pause the video, take 90 seconds, and try this one on your own, and then you can unpause and watch me do it. Okay, first step, we got to swap x and y. So I'm going to rewrite this as y equals 1/3 x minus 2. Then I'm going to swap the x and the y, keep everything else the same. I'm just changing the x and the y. That's all I'm doing. Now I want to get y by itself. So how do I get this guy by itself? I'm going to add 2 to both sides. So x plus 2 is equal to 1/3 y. I'm multiplying by 1/3. I don't want to do that. I'm going to multiply both sides by 3. So this becomes 3x plus 6, and this becomes just y. So the last step to rewrite it in function notation, the inverse of f of x is equal to 3x plus 6. That way I know that these two functions are related. This one is the inverse of this one. All of the ones we've been doing so far have been linear, but you can find inverses of nonlinear functions also, so functions that aren't lines. So here's a parabola, for example. Graphically speaking, we're just reflecting every point across the line y equals x. So it kind of ends up, you can think of it as kind of rotating 90 degrees, but really it's a reflection. And we get this sideways parabola, x equals y squared. Over here we have a cubic function. This blue one is cubic. If I were to reflect that across this line, we get a cubic turned on its side. Kind of looks like this weaving helical pattern. That's not really what's happening. And we get the cube root of x. Okay, so not all of these are functions. So if we look at this first one, the blue graph is a function, right? It would pass the vertical line test. Wherever I draw a vertical line, it will only cross the graph once. However, the inverse crosses the graph twice. So it is not a function. Over here, these are both functions. Wherever I draw the line on the red one, I'm only going to cross it once. So this one is a function. This one is not a function. We'll talk a little bit more about that in a second. Let's find the inverse of a nonlinear function. So let's call this y is equal to x squared. I'm going to swap x and y, right? But now I want to get y by itself. So how do I undo squaring something? You got to take the square root of it. So the square root of x is equal to y. So the inverse of g of x is equal to the square root of x. Now let's think about that for just a second. Let's pop over here. What's the square root of 9, for example? Hopefully you said 3, but hopefully you said plus and minus 3, right? Because the -3 is also a square root of 9. So I had one input, but I got 2 outputs instead of just one. And that's not normal, right? How, if you're thinking in terms of a function, think back to that box we had. When I plug in 9, I get plus and minus 3. How do I know which one to use? Right? That's what's happening in this graph too. When I plug in 9 over here, I'm getting positive 3 and -3. How does that work? That doesn't make any sense. So this is not actually a function unless, when we graph it, we are only talking about the positive side. That is a function. This negative side we don't usually include because it wouldn't be a function. So strictly speaking, this is not a function because you end up with this kind of situation where the vertical line test won't work. If we don't include this bottom half of the sideways parabola and we only think about the positive roots, then we can treat it as a function. So whenever you see this written as a function, we are probably talking about this. But if we're asking, is the inverse of y equals x squared a function? The answer is no, because the inverse would include this bottom part, and it would fail the vertical line test. Okay. So if you don't want to find the inverse first and use a vertical line test, we could use a horizontal line test, because that horizontal line, when we reflect it across y equals x, becomes a vertical line. Right? Just like we turn this on its side, we would turn that line on its side also. So if the function passes the horizontal line test, meaning the horizontal line can only cross it once, then it will be a function. So here's the cubic graph for something that looks cubic. If I draw a horizontal line, it's only going to cross one time. So the inverse will be a function. Here's a parabola, y equals x squared. The horizontal line crosses twice. The inverse is not a function. Now, this graph still is a function, right? Because to check a graph, we use a vertical to see if this is a function. What I'm testing is to see if the inverse is a function. I don't have the inverse yet, so we have to use the horizontal one. If I'd already graphed the inverse and found that it was this guy, then I would use the vertical line test. But if I'm testing the original function to see about the inverse, we use the horizontal. Horizontal line test is for finding inverses, and the vertical line test is for testing the function itself. Okay, so I'm going to make this a yo-yo. You're on your own. Pause this and take 2 minutes. Find the inverse of this function, and then determine whether or not it is a function, whether or not that inverse is a function. Okay, so pause this, 2 minutes, then come back. Okay, y is equal to 2 times the square root of x minus 3. I'm going to move over here so I have more room, and I'm going to swap x and y at the same time. So x is equal to 2 times the square root of y minus 3. It's important to notice that that 3 is under the square root also. So first thing, I'm going to divide everything by 2. So x over 2 is equal to the square root of y minus 3. Now, I have a square root, and I don't want a square root. So to undo a square root, I square it. Got to do that to both sides. On the left, when I square a fraction, you can square the top and square the bottom. And on the right, I just have y minus 3. Now I want to get y by itself. So let's move the 3 to the other side. So x squared over 4 plus 3 is equal to y. Last step is to rewrite it in the original function notation. This function was named h, so we will name our inverse h, but the inverse is x squared over 4 plus 3. The question is this a function? Well, I've seen an equation like this before. I could write it as 1/4 x squared plus 3. Right, that's just a quadratic. So that's going to be a parabola that's 1/4 as steep and 3 units up. So it's just going to look something like this. Is that going to be a function? Yes, this will be a function. That's it. You're on to your homework. Good luck.